Here's a problem that uses molecular orbital theory to calculate bond order and determine whether a substance is diamagnetic or paramagnetic. It says, use molecular orbital theory to describe the bonding in the following. For each one, find the bond order and decide whether it is stable. Is the substance diamagnetic or paramagnetic? So let's take just a second to talk about what molecular orbital theory is. The last time we talked about orbitals, we were talking about how electrons smeared around nuclei. They fly really fast, around 2,200 kilometers per second around an atom, and so they sort of form they smear into these clouds. Each of those clouds is how an electron flies around an atom, and so it's called an atomic orbital. Remember that when electrons fly at lower energy levels, they tend to fly in spheres, like these s orbitals here, and at higher energy levels, they would start to fly in sort of peanut shapes, like the p orbitals. So these are all atomic orbitals because they tell you how an electron flies around a single atom. But these atomic orbitals can start to overlap with each other to give you bigger orbitals. Those bigger orbitals that cover more than one atom are molecular orbitals. They tell you how electrons, especially ones in bonds, fly over multiple atoms, not just a single atom. And so they're called molecular orbitals. So for example, if two orbitals, atomic orbitals, come together and overlap with each other, they can, if the electrons are attracted to the other atom's nucleus more than the electrons repel each other, then they overlap in a way that lets them both fly around both nuclei. And so here you can see how these two s orbitals are coming together and overlapping to give you this bigger sigma orbital. This bigger orbital, it's named by the Greek letter sigma. Now, that helps the atoms stick together, and so it's called a bonding orbital. You can also imagine these atoms coming together and the electrons repelling each other more than they're attracted to the nuclei on the other atom. In that case, you would form what's called an antibonding orbital. You'd have an orbital like this, where the clouds the electrons are moving in are repelling each other, pushing in opposite directions, and that would be antibonding, because it's trying to make the atoms fly apart. So, notice that the antibonding orbital has an asterisk or a star next to it. Anytime you see that star, that asterisk, it will mean that the orbital is antibonding, and if an orbital doesn't have that star, then it's a bonding orbital. So the other atomic orbitals can mix together to give you even more molecular orbitals. As shown here, notice that all of the orbitals that don't have a star or an asterisk are bonding orbitals, and all of the orbitals that do have a star or an asterisk are antibonding orbitals. All of these orbitals together that result from the overlap of atomic orbitals are molecular orbitals, and they tell you all the different ways that electrons can fly over multiple atoms. Now, in these problems, we're going to be thinking about bonding, and bonding only happens in the valence shell. That's the outermost level of electrons. So here, that's going to be the second energy level in this diagram. So I'm going to get rid of that first energy level, and this is what we're going to use to solve problems involving bonding. Okay, so the question first asks to find the bond order. The bond order is 1/2 times the number of electrons in bonding orbitals. Those are the electrons that make the atoms want to stick together to form the molecule, minus the number of electrons in antibonding orbitals. Those are the electrons that make the atoms want to fly apart. So overall, this is telling you how much the two atoms want to stick together. In other words, how strongly they're bonded So that's what the bond order is, telling you how strongly they're bonded. Notice that in this view of bonds, you don't just have a single bond, a double bond, and a triple bond, but you could have anything in between, a 1.3 bond, a 7.9 bond, depending on what you get out of this equation. So let's try to draw the molecular orbital diagram for the molecule C2+. So it's made from two atoms. I'm going to write one atom on the left, the carbon, another atom on the right, the other carbon. Each of these carbons has 4 valence electrons because they come from column 4A on the periodic table. So I'm going to use those electrons to fill in their atomic orbitals. So there's 1, 2, 3, 4. Remember, you filled them in from lower energy to higher energy, and when you have multiple orbitals, you put an electron in each, or one electron in each orbital before you start pairing them. So 1, then that energy level only has 1 orbital, so you pair it, go to the next one, 3, and then fill it up with another orbital. Okay, so here I have my atomic orbitals clearly drawn and organized. And I'm going to use the electrons in atomic orbitals. I'm going to use these electrons in atomic orbitals to fill in the molecular orbitals. So I see, for example, for the 2s, on the 2s energy level, I have 2 electrons from this one carbon, 2 electrons from this other carbon, so 4 electrons total. I'm going to use those 4 electrons to fill in this first level of molecular orbitals. So that's 1, 2, 3, 4. Now I'm going to go to that second level of energy. I have 2 electrons from this carbon. I have 2 electrons from the carbon on the right, so that's 4 electrons total. I'm going to use that to fill in these orbitals, 1, 2, 3, 4. But remember, this molecule has a plus charge, which means it must have lost an electron. So I'm going to take 1 electron, take it away, and this will be my molecular orbital diagram for this molecule. So I can use that to find the bond order. First, I need to find the number of bonding electrons, or a number of electrons in bonding orbitals. Those are all the electrons that are in orbitals that don't have that star or asterisk next to them. So here you can see that I have 5 electrons in bonding orbitals. Then I want to subtract the number of electrons in anti-bonding orbitals. Those are the number of electrons that are in orbitals that have the star or asterisk. Here you can see we have 2. So the bond order is going to be 1/2 times 5 minus 2. That's 1/2 times 3, and so 1.5. So the bond order is 1.5, and these 2 carbons are going to be held together by a 1.5 bond. Now, the next question is to decide whether that's stable or not. Is that molecule going to stay stuck together? So the bond order could either be positive, 0, or negative. And you want to think of it as separated between positive and 0 and negative. If you have a positive bond order, the molecule is stable. The atoms are going to want to stick together. If you have a 0 or a negative bond order, the molecule is not stable. The atoms are going to tend to want to fly apart. So here we have a positive bond order, and so the molecule is going to be stable. Finally, we need to find out whether the molecule is diamagnetic or paramagnetic. If a molecule is diamagnetic, it means that all of its electrons are in pairs. A molecule is paramagnetic if at least 1 electron is unpaired. So let's look back at our molecular orbital diagram. You can see that that bottom orbital has paired electrons. The next highest orbital also has paired electrons. The next highest orbital also has paired electrons, but that last orbital has an unpaired electron. And because this molecule has at least 1 unpaired electron, it's going to be a paramagnetic substance, which means it will be attracted to magnets. So that's the answer for this problem. See if you can follow the same steps for these other problems, and if you have any difficulty or if you'd like to check your answers, I highly encourage you to come into the Student Learning Center in the Boca Tech building, that's BT. on the second floor in room 207. Otherwise, thank you for your attention.